Okay, so today we're going to draw some Lewis structures. So let's take a look at sulfur diphosphide. First step is to count how many valence electrons we need in this molecule. Well, sulfur has 6 valence electrons, and fluorine has 7 electrons. Since there are 2 fluorines, we have to take 7 times 2. That is equal to 14. 14 plus 6, we have to show a total of 20 electrons in this molecule. The next step is to draw the simple skeletal structure. Sulfur is going to be in the middle. We have fluorines on each of the ends. So as you can see, we have already used 4 electrons. 2 electrons for this bond and 2 electrons for this bond. So since we already used 4 electrons, we will subtract it from the total valence electron count. So 20 minus 4 electrons, we have 16 electrons left that we need to add. So adding our 16 electrons, we will always usually add it from the outside in, from the outside atoms first, until the atoms obey the octet rule. So 1. We have 4 electrons we have to put in, so they must be on the sulfur. So now we have a total in this molecule of 20 valence electrons. Okay, so how do we know when we're finished? Well, again, first is the octet rule. Making sure that these non-metal atoms have at least 8 electrons around them. And they do. Each of the fluorine has 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the sulfur has 8. 1, 2, 3, 4, 5, 6, 7, 8. So that is the first rule that we have now satisfied. But before we leave, we must look at the formal charges, because in the long run, when we do more difficult Lewis structures, we're going to have to do formal charges. So let's figure out the formal charges of this molecule right now. Okay, so this is how we do formal charges. Sulfur here has 6 valence electrons, and fluorine has 7 valence electrons. Now if we look at this drawing as written, as drawn, how many electrons is sulfur contributing to this molecule? 1, 2, 3, 4, 5, 6. 6 minus 6 is equal to 0. And how many electrons is each fluorine contributing to this molecule as drawn? 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is equal to 0. Okay, so now remember, just taking a more detailed look at this. In each of these bonds, there are 2 electrons. The atom on the right is contributing this electron, and the atom on its left is contributing to here, that electron. Since the formal charges of all the atoms in this molecule has a 0, 0, and 0 formal charge, this is a very stable molecule. Nature likes the central atom to be 0. If the central atom is 0, then you are finished. Then this is basically the Lewis structure for SF2. The next molecule we're going to look at is boron trihydride. First step is to count the number of total valence electrons. Boron is going to have 3 valence electrons, and hydrogen will have 1 valence electron, but since there are 3 hydrogens, 1 times 3 is equal to 3. We add this and we get a total of 6 valence electrons in our molecule. Second step is to draw out the simple skeletal structure. So hydrogens are always on the outside because they are so small they can only handle usually only one bond. So this is our simple skeletal structure, and we have actually used all 6 electrons since there are 2 electrons per bond, 3 bonds. 3 times 2 is equal to 6 electrons. Now you might think, well, how can boron, it does not have 8 electrons around it, so it is breaking the octet rule. Well, there are 2 elements on the periodic table that can be very happy or very stable with only 6 electrons around it. They are boron and aluminum. So they can have 6 electrons. So they are stable with less than 8 electrons. So to illustrate the formal charges, I will draw out the electron that boron is contributing to the molecule, and the yellow electron is the electrons contributing by each of the hydrogen. So this is the Lewis structure for boron trihydride. So let's look at another molecule, Phosphorus Trisulfide, and it is an anion. At least it has a negative charge to it. It is not a neutral molecule. So first step is to figure out the number of valence electrons in this molecule that we need. So phosphorus has 5 valence electrons, and sulfur, each sulfur has 6 valence electrons, and there are 3 sulfurs. So 6 times 3 is 18, plus the 5 from phosphorus, and we have 23, but because of this negative charge, we add another electron, we get 24 electrons total that we need to show in our diagram. Okay, so the next step is then write the simple skeletal structure. Phosphorus is in the middle, sulfurs are on the outside, and by drawing this skeletal structure, we have already used up 6 electrons, so 24 minus 6 is 18 electrons left. And we will add these electrons from the outside atoms, and if anything is left over, we'll add it to the phosphorus. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have added our 18 electrons. So before we leave, we have to make sure we follow the first rule, which is the octet rule. But as you can see, we have a problem because phosphorus only has 6 electrons around it. 1, 2, 3, 4, 5, 6. So we need to do something about it. We cannot add any more electrons. We have already added 24 electrons total. So for phosphorus to have 8 electrons, we will have to borrow a pair of electrons for one of the sulfurs and make a double bond. Writing this structure. So now does everything follow the octet rule? So phosphorus now has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. So does each of the sulfurs have 8 electrons around it? Let's check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes, now all the atoms in this molecule as drawn follows the octet rule. The next rule we have to figure out is formal charges. So, looking at the formal charges, phosphorus has 5 valence electrons. How many electrons is phosphorus contributing to this structure? Well, if we look at it, phosphorus is contributing 1, 2, 3, 4 electrons to this molecule. So phosphorus here has a positive 1 charge. Well, how about the sulfurs? We have two types of sulfurs. We have this sulfur with a double bond, and these sulfurs here with a single bond. So let us designate that as this is sulfur A, and these two sulfurs here are sulfur B. So in sulfur A, which has 6 valence electrons, how many electrons is it contributing to this structure? 1, 2, 3, 4, 5, 6. 6 minus 6 is equal to 0. How about sulfur B? Again, each sulfur has 6 valence electrons. It is contributing 1, 2, 3, 4, 5, 6, 7. So sulfur B is contributing 7 valence electrons. So the sulfur Bs have a negative 1 formal charge. So this tells us we are not finished yet, because like I said before in our previous molecule, nature wants to have the central atom to be 0. And here phosphorus does not have a 0 formal charge. It has a positive 1 charge. So we have to do something about it if we can. So to do that, phosphorus is going to take another pair of electrons and make a double bond here. So it will look now like this. So now phosphorus, what is the formal charge on phosphorus? 1, 2, 3, 4, 5. So 5 minus 5 is equal to 0. And we know now that each sulfur, these sulfurs here, will have a 0 formal charge. This sulfur here, let's call that sulfur B, will have 6 minus 7, a negative 1 charge. But that is okay, because again, nature just wants to satisfy the central atom to have a 0 formal charge, and we have done that. So this then is the Lewis structure for phosphorus trisulfide anion. So let us try another molecule, nitrogen dioxide. First step again is to count how many valence electrons we're going to need for this molecule. Nitrogen has 5 valence electrons, and oxygen has 6 valence electrons, and there are 2 oxygens, so 6 times 2 is 12. So the total number of valence electrons we're going to show is 17 electrons. And it is okay to have an odd number. It just means we're going to have a single electron all by itself, and it is called a radical in chemistry, which is perfectly fine. So 17 electrons are going to be placed in the simple skeletal structure, nitrogen, and 2 oxygens here. So now we have used up 4 electrons, 2 electrons per bond, so 17 minus 4, we are down to 13 electrons. We will add these electrons from the outside atoms first, and then anything left over, we're going to add it to the nitrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 1 electron left. We'll put it on the nitrogen. Again, this is called a radical. It is just an electron all by itself in its own orbital. Now, like before, we're going to find out about the octet rule. Let us see if our atoms in this molecule follow the octet rule. Well, each of the oxygens have 8 electrons around it, but the nitrogen, it only has 1, 2, 3, 4, 5 electrons around it, and it wants 8. So we're going to have to do something about that. So we're going to take a pair of electrons and add it here, and that makes this molecule look like this now. So Again, let's see if the octet rule is still being followed. This oxygen has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And now nitrogen. Nitrogen here has 1, 2, 3, 4, 5, 6, 7. So the nitrogen is not following the octet rule. So only 7 electrons. So what can we do? Well, let's see what we do if we take a pair of electrons from the other oxygen and put it here. What will this look like? It will look like this. Again, each of the oxygens is following the octet rule. They have 8, so that's fine. But the nitrogen, if we count how many electrons are around it now, it has 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is not going to be stable at all. 9 electrons are too many electrons around the nitrogen atom. It cannot hold them, so we cannot make 2 double bonds. We have to, again, go back to having the nitrogen only to have 7 electrons. So we're going to have to remove one of the double bonds. It's going to have to look like the structure before. Again, nitrogen is better off having 7 electrons than 9 electrons. So, for nitrogen. Let us check now the formal charges. Okay, so taking a look at the formal charges. Each of the oxygens, let's call this the one with the double bond oxygen A, and this is oxygen B. So looking at oxygen A with its 6 valence electrons, it is contributing 1, 2, 3, 4, 5, 6 electrons in the molecule. So 6 minus 6 is equal to 0. Taking a look at oxygen B with its 6 valence electrons, it has 1, 2, 3, 4, 5, 6, 7. So it is 6 minus 7, has a negative 1 formal charge. And now let us look at nitrogen with its 5 valence electrons, and it has 1, 2, 3, 4. So it has 5 minus 4, it has a plus 1 charge. But again, this has to be the answer because, again, we tried to make it have 5, but the problem is then by putting that extra double bond, it had 9 electrons around it. So we have to be then satisfied with this structure, even though the central atom has a positive 1 charge. That is still okay because we cannot break the octet rule. The octet rule supersedes the formal charges rule. That's why we have to do this first, and then we answer this second. But this then is the Lewis structure for nitrogen dioxide.